In this lesson, we're going to look at some of the pitfalls that sometimes occur when people try to do probability. There are some misconceptions that can occur whenever you give too much thought to something that actually means something different. Here's a very important example. A particular company makes a steroid test that boasts a 99% accuracy of finding steroids in a person who is taking them. An athlete takes the test and tests positive for taking steroids. How likely is it that the person is actually on steroids? Your gut instinct may be to just say 99%, and that is where there is a very common misconception. The 99% is the probability of finding steroids if they are taking them. It's a detection rate, if you will. If it is in their blood, then it will be found 99% of the time. To write it down formally, we don't know, because the 99% is the probability of detecting the steroids if a person is taking them. Now let's go a little bit further. Suppose we read the fine print and discover there is a false positive rating of 10%. What that means is that if the person takes the test and are not taking steroids, they will test positive 10% of the time, even if they're not taking the steroids. How does this change what we think about the problem? This will definitely reduce the chances of being on steroids when tested positive. Now the question for us to ask is, how much does it reduce the chances? Do you subtract it from the 99? Does it mean that it's now an 89% accuracy? Let's go a little further. We can use something called Bayes Theorem that will help us find the actual probability. Bayes' theorem is something that allows us to switch the order of our probability. We were given the probability of a person who has steroids testing positive. We want to know the probability of a person having steroids who tests positive. You'll notice it's not a very big distinction. It's subtle, but it's very important. Without going into the details, this is the calculation that we use for Bayes' theorem, assuming that about 5% of the population who's taking the test is on steroids. If we calculate this and convert it to a percentage, it comes up to a shockingly small number, 34.26%. That's very small. So if they test positive, that false positive rating is so substantial that it drops the probability very low. So to answer the question, probably not, as the probability is unfortunately low. Now what would we do here? Well, the other way to do it is to test them at different times, or possibly use different tests. When you start having things collaborating with each other, then you actually get some accuracy if you have a false positive rating this high. Let's move on to another famous probability problem that came up with a lot of controversy when it first came around. This is called the Monty Hall problem. You have a chance to win a brand new car. What you do is you pick a door, any door, and then that door might have a car behind it. Once you pick your door, your host will open one of the other doors you did not pick, and he shows you that behind that one there is a goat. He knows where the car is, so he's always going to pick a goat. And then he offers you a tempting offer. Do you want to switch your choice to the other unrevealed door? You can switch, you can stay. Either way, open the door, and if you find the car, you win. So the question is, should you switch or should you stay? For my example, I'll pick door number 2. When I pick door number 2, my host opens door number 3 and shows me there is a goat behind door number 3. Well now, should I switch? Should I stay with door number 2? It was my first gut instinct. Maybe I should trust my instincts. But I think I'm going to choose to switch. I switch to door number 1, and look, I won a car, and it's a pretty nice one too. Now, to try this a few more times, if we were in class, I could do an experiment with everybody and let everybody try it. What I suggest you do is Google the following phrase: show door, Monty Hall. Show door has a lot of interactive experiments, and this is the Monty Hall one. The first result, as of the time of this video, is that particular one. If you go to that website, you can see what's going on as far as trying it yourself a few times. Keep trying and just see what's going on. I'm going to run a little experiment myself, and I'll show you what I get out of mine. In my experiment, whenever I stayed, I won 6 times, but I lost 14 times. So out of 20, that's 30% of a win rate. When I switched, I actually won 14 times, and I lost 6 times, for a win rate of 70%. Now this came out really nice. These numbers might not come out as perfect to add to a 100, but you should get something similar. Now isn't that a little bit strange? If we were to stay, we would think, well, there's 2 doors left. There's a 50-50 chance of winning, right? Well, something else is going on here. At the beginning of the game, this is what happens. You have a 1/3 chance of each door having the car behind it. Let's choose door number 1 to keep this simple. If I choose door number 1, that means my probability of winning would be 1/3, and my probability of losing would be 2/3. But then the other door is opened, and the goat is revealed. What's really going on is the probability of my door being a winner is still 1/3. Why should the probability have ever changed? It was 1/3 at the very beginning. But now all the probability of losing has shifted to door number 2. So there's a 2/3 chance of winning if I switch. Now I will give you, this is counterintuitive. It's one of the things that you have to think about and accept. And as a matter of fact, there was even controversy. If you want to read up about it, look for the Ask Marilyn column involving this Monty Hall problem. So now the question is, should we switch and why? Yes, we should switch. The probability of winning with our first door never changed, but the remaining door's probability of holding the car doubled.